Alrighty, well, picking up from where we left off yesterday. Yesterday we went through category number 3 of the KSP types of problems. And that focus was, will it make a precipitate or not? Will the ions essentially find themselves to make a precipitate, or is it kind of like, hey, you dump a gram of this chemical on this side of Hoover Reservoir, I'll dump one on the other side, and then, hey, when the chemicals dissolve, they'll find each other and make a precipitate and will clog the dam. Well, no, probably not, okay? Here we go. Category 1, Category 2, I wish I could have given you more space on that front side, but to me it was very important for Category 1 and Category 2 to be on the same side of the same piece of paper. The thing that I want to call out from the very beginning is, in Category 1, we're going into pure water. Into pure water. Pure water, as you know, is just H2O. There are no dissolved ions in distilled water. In Category 2, I'm going to jump down. I'm going to jump down on the page here. Now, in Category 2, we're going into a common ion solution. All right? And we'll talk more about what that means. But first, we'll knock out category number 1. What you and I both know, and again, I know I'm repeating myself here, but it's tough for me to get it to fit into that little tiny space, so I'm going to cheat, and I'm going to write something up here. I don't know if you need to write it down or not, but it helps me to be able to point to it while I'm mentioning it. What we're talking about is getting calcium fluoride to dissolve. I know when that compound dissolves, it does this. It breaks apart into 1 calcium and 2 fluoride ions. We show that with an equilibrium type of thing, and I'm going to write it here again, fairly small. CaF2 solid is being in equilibrium with its dissolved aqueous ions. Calcium plus 2, AQ plus 2 of the F minus, AQ, for aqueous or dissolved. What I know is that when we first put that into water, there are no ions present in there. A small amount does dissolve. What you know, what I know, if we look at the top left here and we see how the green lines kind of separate the ions, if I were to have, say 4 calcium fluoride molecules, if 4 of them dissolve, I will have 4 calciums and 8 fluorides. How many folks does that make sense? If I have 4 at the beginning, you're getting 2 of the fluorides, okay? If you understand that, what I'm about to do makes perfect sense. So, yeah, Bracken, as this thing dissolves, this is going to go up by X. And then fluoride, I guess that's going to go up by 2X. Because every time you take apart 1 CaF2, you're going to get out 2 of the fluorides. So it's going to do that until it reaches equilibrium, or it becomes fully saturated. That'll be X, and that'll be 2X. Now a reminder, KSP, I had a student earlier today say this, and I thought it was really, really good that the student was getting it. KSP is all about equilibrium. It's all about equilibrium. But the student said, hey, Bracken, you're using that 2 a lot. And I said, well, what do you mean by that? Well, I get it. It's CaF2, and I get it. You're going to have a 2 there. But we use that 2 to go up by 2x. Isn't that enough? No, it isn't. We're going to use that 2 not only here in the 2x, what I've highlighted, but it's also going to show up in the squared. And that goes back to when we were first learning about equilibrium. Remember, equilibrium, products over reactants, and the coefficients do matter. Okay? The problem is in the acid-base unit, we had a lot of coefficients of 1, 1, 1, 1, 1, 1, so we never had to really remember that. Okay? Watch how easy this is. We're going to take this, we're going to say Ksp, the number is listed there, 3.9 times 10 to the minus 11. That's equal to the molarity of calcium, which is here, X, times the molarity of the fluoride ion, 2X, and we're going to square that. Now be careful here. It's possible, especially here at the end of the day, 10th period, it's possible, if you're tired, like I kind of feel at times, if you look at that really fast, you may make a math mistake that you shouldn't. I'm going to write it down here and then erase it. So I don't think you need to write it down. But I want to make sure that we agree that this would look like this if we were to write it all out. It's 2x quantity squared, okay? If you see it this way, what I'm about to write up here, oh, okay, I see what you did. 2 times 2 is 4. X times x times x is x cubed. So this is going to wind up being 4x cubed is equal to that 3.9 times 10 to the minus 11. Okay? So that, again, 2x quantity squared would be 4x squared times x, 4x cubed. Now, there are different ways of using the graphing calculator to solve for that. You could, the way I would do it, divide both sides by 4, take the cube root. Other folks are like, solver function, here we go again, and that's fine. But what we would get at the end of the day is x is equal to 2.1 times 10 to the minus 4. That's the maximum molarity of calcium fluoride. All right? Now, since I don't have a lot of space, I'm going to erase this. Don't erase it in your, I want to write that number out so you can see what that looks like. All right? I want you to see what that number looks like because it would be possible to not see what that means. That is a very small molarity. Very small molarity. And that's as big of a molarity as we can get to make a solution of calcium fluoride. That a cruel joke that a chemistry teacher could play on his or her students would be to say, hey, go back there and weigh out enough stuff to make a 0.1 molar solution of calcium fluoride. And the students could crunch the numbers. They'd get that many grams. They'd come in, and they might have it in an Erlenmeyer, and they'd swirl. And as a teacher, you'd be like, well, sorry, no credit until you get that to dissolve. When's it going to dissolve, Bracken? Actually, never, because you can't get it to, it's not that soluble. So, yeah, very, very insoluble compounds. Now, a reminder, I think this is a good time to remind everybody, I've said it, I think, every day since you got the pink sheet. Pink sheet chemicals would be considered in a yes-no world. That's not soluble. Yeah, it is. 0.0021 molars, as big as the molarity can get. Oh, okay. So a teeny tiny amount will dissolve in a large amount of water. Yes, and that sums up the entire pink sheet. Okay? Now, let's go on to problem number 2. We're talking about a saturated solution of sodium chloride. You saw that earlier this week. And they tell me the molarity is 5.65. So I'm going to write NaCl brackets. That's equal to 5.65 molar. Oh, let's see. Who should I call on today? I'm really thinking it's time for a no. How you doing? Super. Hey, question for you. Well, we know the molarity of a saturated solution of sodium chloride is 5.65 molar. My question for you, what would be, if I could look inside that solution, what is the molarity of just the Na plus? Absolutely. And then you would agree chloride would be the same, right? Get one out of each one. Yep. That makes sense to me. Well, they want to know, in this problem, they want to know what is the Ksp value. So for me, I think, well, Ksp describes the solubility process. I better write that. So I'm going to write NaCl solid is going to be in equilibrium with its dissolved aqueous ions. The dissolved ions, as what Ano just said, hey, that's going to be 5.65, and that's going to be 5.65. Ksp, if that's the equation, Ksp is equal to Na plus times Cl minus, because there aren't any coefficients. So then, oh, well, that's easy enough. Ksp is going to be 5.65 times 5.65. And when I did the math on that, I got a final answer of 31.9. Now, I love that problem because I remember doing it for the first time many years ago. I crunched the numbers. Up pops 31.9, and I'm exceedingly uncomfortable with that large of a number. I'm uncomfortable with it because I've looked at my pink sheet. Well, sodium chloride is not on here, but I've looked at my pink sheet, and these numbers for Ksp are incredibly small. 2 times 10 to the minus 53. Holy smoke-a-doodles. Those are really small numbers, and I'm cranking along at 31.9? Here's what I then remembered after I double-checked my calculations. Wait a minute. The pink sheet chemicals are all, hey, that's not soluble. We all know that table salt, NaCl, is going to be soluble, very soluble. And so when you say something like, oh yeah, it doesn't have an unlimited solubility, but you can crank out a 5.65 molar solution. Oh wow, that's really soluble. We tend not to use the concept of Ksp with things that are very soluble. So while I was very uncomfortable with 31.9, after I thought about it, that makes sense. The bigger the Ksp, the more soluble a substance is. Or we can go the other direction. 2 times 10 to the minus 53, holy smoke-a-doodles, that's not very soluble at all. The smaller the Ksp, the lower the solubility is. That made sense to me, okay? Hopefully it makes sense to you as well. But that's a big number because it's got a rompin' stompin' 5.65 molar saturated solution molarity. Right? Let's go to category 2. Category 2, the first thing I'm going to do is I'm going to draw, and you'll see Bracken artwork here. The idea was to draw a beaker. But I can tell you that my beaker would take the entire thing. Mine is going to look more like, hey, let's go to Meijer and buy the backyard pool for the 2 little toddlers to play in. It'll fit in the back of the Honda Pilot, and life is good. So it's going to look more like this for me, okay? There's a beaker, all right? Again, I know it looks not really like a beaker, but we'll make it work. And I'm going to draw a little blue water line there, because I want you to have a visual here for what this next problem is. Hey, it contains 0.75 molar NaCl. So I'm going to label it. I'm going to write 0.75 molar NaCl right there. Okay, and in fact, I'll draw a little arrow. So like, hey, that's what it is. I also, knowing NaCl is going to dissolve in water, no problem, I'm going to write free swimming Na plus, free swimming Cl minus. I'll do Na plus here, and I'll do Cl minus there. It's already down. up above. What I want you to think about is we're going to add some solid AgCl crystals. So I'm going to write up above here Ag plus Cl minus, and I'm going to go ahead and circle those two. As I think about this, they're wanting me to get the molar solubility, or what is the maximum molarity of AgCl. Since we're talking about solubility, I think I'm going to have to write, in fact I am going to write, the dissolving chemical equation for that. AgCl solid, arrow, double arrow, Ag plus, it's aqueous, plus Cl minus aqueous. Kyle, got a question for you here. How you doing today?
A little tired.
Well, don't you worry. This will wake you right up. Hey, I feel like I'm going to drop some of this AgCl powder into the water down below. Okay? I'm going to add that, and I want you to picture it. It starts to drop down, and all of a sudden I take a picture of it. Okay? The powder has not yet broken the surface of the solution below. Okay? At that moment, and if we think of it as like a feather, you know, hey, it's going, you stop action. What is the molarity of the Ag plus down below?
In the solution, you mean?
In the solution.
Here.
You are correct. Okay? Because there's no Ag plus down there. So you're starting from 0. But Kyle, what's the molarity of the chloride ion?
0.75.
Exactly right. Okay. A show of hands, how many folks would have gotten those two questions right? Okay. This is the hardest part of the day today. Okay. So if you see that, you should be like, okay, this is easy. An analogy that I think has helped some. Hey, when you open up a bank account, 2 ways to do it. I have no money to put in, or I just opened it. Oh, you don't have any money? Well, no, I put $75 in to hold the account. Oh, okay. So I'm not starting from scratch with respect to Cl minus. There's some pre-existing chloride down there already. Now, it does drift down. It does drift down all the way into the water, and a small amount does dissolve. Well, we know if you're adding AgCl, whatever does break apart, oh, you are going to go up by X, and you also are going to go up by X. And eventually it will reach equilibrium, where that is X, and that is 0.75 plus X. It's easy enough. The Ksp value is listed at 1.8 times 10 to the minus 10. And we know that Ksp, equilibrium constant, is all about the equilibrium line. Not a problem. So that is going to be equal to X times 0.75 plus X. When I did the math on that, I got X is equal to 2.4 times 10 to the minus 10. And I do want you to see, you do not need to write this down, but what does that number look like? 9 zeros and then 24. Reminder, this is the maximum molarity that can exist when we try to dissolve AgCl into a 0.75 molar silver or sodium chloride solution. For all practical purposes, we would say that won't dissolve. Okay? you might need a swimming pool to get a small amount to dissolve, but that is the maximum molarity of AgCl that will dissolve. Okay? Easy enough. Here we go. Last example. We're talking same idea. We're going to put calcium fluoride into some KF solution. Reminder about the category. I'm going to go up. Whoop. We're going into a common ion solution. In other words, dissolving it into something, it's not a coincidence that there's fluoride here and fluoride with the KF. It is not a coincidence. Here we go. Let's describe that solubility reaction. CaF2 solid, double arrow, Ca plus 2, aqueous, plus 2, F minus, aqueous. And it's already starting with 0.50 molar Kf. What the business end here is 0.50. As Kyle pointed out, if you haven't added any calcium to it yet, that's a 0. All right. Well, when some of it does dissolve, we're going to get X there, and this is going to go up by 2X. Because I get 2 fluorides out of each calcium fluoride compound. Therefore, at equilibrium, 0.50 plus 2x, Ksp is equal to 3.9 times 10 to the minus 11, and that's going to be equal to x times 0.50 plus 2x squared. Solver function will take me across the finish line. X is equal to 1.6 times 10 to the minus 10. Maximum molarity. Okay. Essentially insoluble. Now, what we're going to do is we're going to go right into worksheet number 2, and I want you to be comfortable